In the summer of 1968, Gabrielle Veneziano, an Italian physicist, was attempting to discover the strong nuclear force. And while doing so, he came across a 200 years old equation written by Leonhard Euler, and saw something in it that no one else could. The formula perfectly described the force, the glue that binds quarks together. And then, while being a visitor in CERN's theory division, Veneziano wrote a paper about it. But later, Leonard Susskind, also a physicist, found out that at its heart, the formula was describing not just the physics of protons and neutrons, but strings that could vibrate. Veneziano accidentally gave birth to string theory with his paper. Today, we'll delve deep into the different versions of string theory and extra dimensions and attempt to answer a question: was this discovery a good accident or a bad one? I'm Hamza Ijaz and you're watching Astrobytes. Let's dig deeper. First of all, let me explain what string theory actually is and why it caused so much excitement in the physics community. We're all familiar with general theory of relativity and quantum mechanics. The first one describes matter and energy at the large scales. It tells us that energy and mass are interchangeable, that space and time are warped together, that gravity is actually a property of the fabric of space-time itself, and much more. Quantum mechanics, as we know, explains stuff at the smallest scales. It handles electromagnetism, the weak nuclear force, and the strong nuclear force. It tells us that a particle is actually a wave of probability. You can predict events with precision using Einstein's and Newton's equations. Their theories provide definite outcomes, while quantum mechanics only gives probabilities. And somehow unifying these two radically different theories can give us the theory of everything. The only problem is it's not very simple. When we try to add gravity to our standard model of physics, our mathematics breaks down and we get infinite values that we cannot get rid of. It is in some way like dividing by zero. Scientists have been trying to solve this puzzle for many decades and have come up with different theories. At present, the most promising and useful model seems to be string theory, which says that the subatomic particles, all of the electrons and quarks, are made of incredibly tiny vibrating strings. Different modes of vibrations of a guitar string produce different notes. Likewise, the distinctive vibrational mode of one particular string produces a certain particle. A string can have one or more ripples and it can be open or closed. If it vibrates in one way, you have one particle. And if it vibrates differently, you have another particle. What makes this theory even more fascinating and worth studying is the fact that one of the strings vibrates like a graviton, the particle of gravity, thus describing gravity at the quantum level. Problem solved, right? Well, not exactly. The bosonic string theory, the version of the theory we just learned about, comes with three problems. It predicts the existence of a particle with a negative mass, named tachyon. It's a particle that is thought to have a velocity exceeding that of light. The strings only behave like bosons, like photons and gravitons, and the model doesn't include the other category of particles that exists in our universe, fermions. The third and last problem is that it requires 26 dimensions to work, but we are only familiar with 3 dimensions of space and 1 dimension of time, right? Is there a solution? Luckily, yes. By putting spinors on the strings, we solve many problems. First of all, the tachyon doesn't exist anymore. Secondly, we get strings that act like fermions. What's even more astonishing is that it predicts that there are as many types of bosons in the universe as there are of fermions, that every particle in the standard model has a superpartner. This is called supersymmetry. Elegant, right? This supersymmetric string theory, or superstring theory for short, also requires a less number of dimensions, 10. But apparently there are still 6 extra dimensions that we have never detected. How do we remove them? Turns out we don't have to. These hypothetical dimensions might tell us something fundamental about several phenomena, like the nature of gravity. One possibility is that gravity is very weak compared to the other forces because it is diluted in these extra dimensions. But where are they? Maybe they're just too large and complex for 3-dimensional beings like us. To get a better understanding of it, let's take a look at Edwin Abbott's 1884 classic novel, an unusually captivating tale, Flatland. The characters are line segments, polygons, and all sorts of shapes. One character is a square, who is a mathematician and a resident of the 2-dimensional world, and at some point in the story is visited by a 3-dimensional sphere. Here, the sphere is a superior being. It can see through the buildings and inhabitants of this flat world, but all that the bemused poor square can see is a slice of the sphere, a disk. As the sphere moves up, the disk grows smaller in size and shrinks until it becomes a point and vanishes. When the sphere says something, it seems to the square that the voice is coming from all directions. Even after the sphere has done everything in its power to convince the square that he is indeed a sphere, the poor square fails to comprehend the concept. And then, the frustrated sphere takes the square out of his frame of reference and transports him to space. The square is astonished as he looks down at Flatland and yells, "Either this is madness or it is hell." The sphere replies, "It is neither, it is knowledge." When the poor square returns to his world, he shares his experience with other Flatlanders about visiting a higher dimension. But when asked for an explanation, he fails to convince them of the existence of such a dimension, as he cannot point to where it is. So he is sent to jail as a heretic. Anyway, we find ourselves in a similar situation. We cannot imagine a higher dimension because we are locked in a four-dimensional world. But the most promising approach to this seemingly irremediable problem of extra dimensions, and the most widely accepted idea, is that these dimensions that we cannot see are curled up on themselves, and they are so small that only the strings are able to experience them. Let's try to explain it simply with an example. Imagine an ant crawling on the surface of a straw. From afar, the straw looks like a straight line, a one-dimensional object, uninteresting and ostensibly unhelpful in your goal to discover the ultimate theory. But in reality, the ant can loop around the straw and can hence experience another dimension, the one we failed to detect. Now one might think that there are infinite ways that these dimensions could curl in on themselves. For example, take a piece of paper. You can fold it in countless different ways. You can make a plane out of it, a donut, almost anything. But these compact dimensions actually follow certain geometries called Calebi Yao manifolds. Although the number of such manifolds allowed by string theory aren't infinite, there are still a lot. 10 to the power of 200,000. Now that is a plethora of unique possible manifolds. Here's where it gets even more amazing. The way that these dimensions are curled up affects the vibrational modes of the strings that are moving inside them. And as we know that the vibrating mode of a particular string is what we interpret as a certain particle. So each manifold corresponds to a distinct universe with its own unique laws of physics and a radically different set of particles. String theory at this point has predicted a multiverse, universe after universe, until every single possibility is played out. But we just cannot know which manifold corresponds to our universe and why it contains the particles we're familiar with, and not some other particles. And that brings us to the question, is the theory worth it? And secondly, the excitement about it has been withering away, since physicists haven't found any supersymmetric particles at the Large Hadron Collider. I actually asked a particle physicist working at the LHC about the possibility of finding one in the future. And she said, some scientists are hopeful we'll find them with the LHC, others have already started looking to the future. I'm pragmatic, she added, and we'll just have to see what nature has in store for us. It's just a matter of when. Maybe it's just that to find such particles we'll need collisions with much more energy. Well, our galaxy has pretty big particle accelerators. Gamma ray bursts are the most extreme events in the universe and are very efficient particle accelerators. When a star goes supernova, its magnetic field channels most of the energy into two jets of plasma, one at each pole. Scientists believe them to be a source of the cosmic rays that hit Earth's atmosphere. They're ultra-high energy particles, most of which are photons. When these cosmic rays are traveling through space, they interact with the photons of the cosmic microwave background radiation and they lose their energy because of it. But sometimes, these interactions can give birth to high-energy neutrinos, having energies up to 10 to the power of 20 electron volts. CMB isn't a hindrance for them. As we know, neutrinos are tiny ghost-like particles that can pass through anything and everything. 100 trillion neutrinos are passing through your body every second. In fact, they can pass right through Earth. But very rarely, while passing through our planet, they can interact with the atomic nuclei, an extremely rare event in which a high-energy neutrino decays into a shower of particles like electrons and muons, and a flash of visible light is produced on the ice sheet. This has a name, Cherenkov radiation, which is created by a particle traveling through a dielectric such as ice at a speed faster than the phase velocity of light. Sounds just like the phenomenon we talked about, right? So how do we detect these? Meet ANITA, the Antarctic Impulse Transient Antenna. It's an array of radio antennas flying over Antarctica at a height of 37 kilometers with the help of a high-altitude helium balloon. When an ultra-high energy neutrino interacts with an atom in the ice sheet and decays into secondary particles, the Cherenkov radiation produced, which only lasts for 1/billionth of a second, can be detected by ANITA. But the results weren't as good as physicists thought, but some findings are very intriguing. It detected cosmic rays coming out from the ice, leaving Cherenkov radiation on the surface, and these beams were made of particles never seen before. which filled the particle physics community with excitement. IceCube Neutrino Observatory, an experiment which also looks for ultra-high energy neutrinos, had already detected these unknown things thrice. As always, everyone had different explanations. Some argued that the particles were just sterile neutrinos, but a paper published by Dr. Derek Fox and his colleagues at Penn State University says otherwise. After looking at the data collected by different observatories, the researchers at Penn State University calculated that there was only 1 in a 3.5 million chance that a particle detected is part of the standard model. Dr. Fox and his colleagues think that the particle is a tau lepton, the theoretical supersymmetrical version of an SM particle, the tau lepton. The name of an SM particle's superpartner is obtained by simply putting an S in front of it, like the supersymmetrical version of a quark is a squark. Dr. Fox also said that a data present isn't enough to be certain. If proven right, SUSY can solve many problems in particle physics and help us understand dark matter, which is thought to be composed of undiscovered particles called axions. Sayeda Ipek, a theoretical particle physicist from UC Irvine, says even though the SM works very well in explaining a plethora of phenomena, it still has many handicaps. For example, it cannot account for the matter-antimatter asymmetry of the universe. There are 5 versions of string theory: Type 1, Type 2a, Type 2b, SO32 heterotic, E8 times E8 heterotic. All of these theories predict different types of strings. In 1995, Edward Witten showed that the 5 theories are in actual fact limitations of a single more fundamental theory, connected by S and T dualities. Unlike the superstring theories, M theory takes the number of required dimensions to 11 and also includes supergravity. According to Witten, the M should stand for magic, membrane, mother or mystery, and that the name should be finalized when the theory is better understood and a more foundational formulation of the theory is discovered. String theory has helped develop many fields of mathematics and has assisted us in the study of black holes. The theory has also been quite useful in fields like nuclear physics and early universe cosmology. It might or might not be the perfect picture of reality, but can definitely be thought of as a highly valuable piece in an enigmatic puzzle which is still being solved.